Hi everyone, our topic for the next few lectures is going to be nonlinear solvers. Just like we learned about linear solvers, where we solved linear systems of equations, now we're going to learn about methods to solve nonlinear equations, and we call this nonlinear solvers. Before we get started, I want you to go ahead and download the following Jupyter notebook so that you have it ready as we go to our coding activities later on. The learning objectives for this chapter are quite a handful. You will learn how to define a nonlinear equation, what a nonlinear equation is, define what's meant by solving the equation f of x equals 0, define and write down the residual form of an equation, define what is meant by the root of an equation, define closed and open domain methods for solving nonlinear equations, calculate the roots of an equation using four methods: bisection, false position, secant, and Newton's methods. Define a system of nonlinear equations, linearize a system of nonlinear equations. So first we're going to learn how we solve a single nonlinear equation, and then we're going to look at coupled or systems of nonlinear equations. Calculate the roots of a system of nonlinear equations, geometrically interpret the roots of a system of nonlinear equations, and define the Jacobian matrix, what is meant by that. So first, let's set the stage with a realistic example. We're going to consider a parachutist in free fall, and the motion of this parachutist, of this person, is subject to Newton's laws, Newton's second law, and it says that the summation of forces applied on the individual, on the parachutist, is equal to the mass times acceleration, which is du by dt, where u is the speed at which the parachutist is falling. And so we're going to take the positive direction going down, as you know, the parachutist going down in the negative z direction, that is. Now, the forces that this parachutist is subject to is, of course, you have the weight, which is given by Fd here, equal mg, d for down, that's the weight force. Now, in reality, the parachutist is subject to drag. Drag is resistance caused by the air as an object is moving in the air. And the drag force is opposite to the weight force, which is dragging the parachutist down to earth, and we call this F up. One form of the drag force is given by this c times u, and the negative sign is to indicate that this force is in the negative direction, because we assign the positive direction as going down, okay? So now this drag force is in the form of a coefficient times the velocity. We call c as the drag coefficient, and c depends on the profile of the object. So if you consider air moving against these two shapes, for example, this conical shape that looks like a parabolic, like a dish, like a satellite dish, or the flow over a little bump, like the profile of an airfoil. So obviously, intuitively, you'd expect to have more drag for the conical object, for the dish-shaped object, as opposed to the one where there's a little hump. And indeed, this is expressed as a larger drag coefficient on this object versus a lower drag coefficient on this one. Now, the exact solution for this equation in this case is given by this formula: u, the speed of the parachutist going down, equal mass times gravitational acceleration over the drag coefficient into 1 minus the exponential minus c over mt, where t is the time, m is the mass of the parachutist, and again c is the drag coefficient. Okay, now since we're doing this online, I'm going to try to keep up with activities, but I want you to take a minute now and pause the video once I'm done explaining this activity. Take a few minutes, do it individually, obviously, or if you're looking at these in groups, do it as a group. For a 70 kilogram parachutist, what is the required drag coefficient c to reach a velocity of 40 meters per second after 10 seconds of falling? So for example, I'm trying to design the profile shape of the parachute because as we learned from the example of the shapes we looked at earlier, it's the profile of the shape that matters in the drag, in the whether you have a large drag coefficient or a small drag coefficient. What we want here is we want to design a parachute so that the parachutists reach a certain velocity after a certain period of time from jumping, for example, from an airplane. And so our target velocity is 40 meters per second after 10 seconds of falling. And the question is, what is the drag coefficient? And once we know the drag coefficient, we can probably play around in how we design the parachute. And so I want you to look at this equation, and from it, plug in the mass, gravitational constant 9.81, velocity and t, and try to extract a value for the drag coefficient. Take a few minutes, put pause and take a few minutes. Clearly, as most of you have found, is that this is unsolvable because of the way that c shows up in the equation. And we say that c shows up in a nonlinear manner. We couldn't do anything to try to extract c out of this equation. So essentially write c as a function of u and m and g and t. And that's a classic example of a nonlinear equation. So let's now take a step back and remember what we did. We know how to solve linear equations. So take a simple linear equation, ax plus b equals 0. We know how to solve for x. Then we learned how to solve systems of linear equations described by a matrix times a unknown vector equal to a vector of right-hand sides. And we wrote this as x equal a inverse b. We learned how to approximate a inverse, or essentially do iterative solvers to solve the system of equations. We will now learn how to solve nonlinear equations, and these are equations that you cannot extract the value of the unknown from them algebraically by simple algebraic manipulation. Or more specifically, what's a nonlinear equation or function? Now, if you think of the form y equal f of x, if you think of this as the function as being something that processes an input, x, so x is the input, f is something that manipulates or modifies the input to produce an output, y, then by definition, a nonlinear function is one where changes in the input are not proportional to changes in the output. So again, a nonlinear function is one where changes in the output are not proportional to changes in the input. So let's look at an example. Consider these two functions, y equal to x and y equal cosine x. We know that y equal to x is a linear function. One way to interpret this is that it looks like a straight line in the xy plane. And y equal cosine x, we know that's a nonlinear function, but let's kind of look at this definition a little bit more closely. If you evaluate these functions at the point at x equal 1, y of 1 gives you 2, and y of 1 equal, for the cosine function, gives you cosine 1, which is 0.54. Now let's double the input. So x now is equal to 2, so y of 2 is equal to 4. And for the cosine function, y of 2 is equal minus 0.42. So you notice in the linear function, in this case, the proportionality constant is 2, and then we doubled the input, then the output is going to be doubled. That's a classic linear function. For a nonlinear function, we doubled the input, the output did not double. So a linear function output is proportional to the input with whatever proportionality constant. However, with the nonlinear function, there's no saying, it just behaves nonlinearly. But what does it mean to solve an equation, linear or nonlinear, for that matter? So f of x equals 0. You've heard f of x equals 0. What does it mean to solve this equation? I want to look at the geometric interpretation for a second. Take this arbitrary function. Okay, it looks like this kind of crazy looking function. What does it mean to say f of x equals 0? Well, first let me draw a line on the y equals 0 line. So y value equals 0 along the entire x-axis. You see this black line over here. Saying f of x equals 0 means finding these points where f of x intersects the line y equals 0. And we have 3 points over here. Now, we say that solving an equation f of x equals 0 means finding the values of x that make this function f of x equal to 0. And those points are specifically called the roots of the equation. Now here's an activity for you. Locate the root of the blue curve to the left. Take a minute to do it. Okay, so obviously you identified the root as this point. Okay, so now we're going to take this other interesting looking curve, and let's say this curve is given by f of x. Locate the root of f of x equal 10. Take a minute, pause the video, and try to locate the root f of x equal 10. Okay, so what you've probably done is drew a straight line, a line at the y value equal 10 that and found the point of intersection where f of x intersects with the line y equal 10. And in general, the root of f of x equal alpha is the point of intersection of y equal f of x and the horizontal line y equal alpha. Just like f of x equals 0, this is f of x equal 10. F of x equals 0 is the intersection, the root is at the intersection of f of x and the line y equals 0. In this case, it's the intersection of the line of the curve f of x with the line y equal alpha. Okay, and the root is about 6.75 in this case. So let's keep this curve there for a second. And now notice what I've done here. I changed the y-axis values. They changed. Now they go from -10 to 10. And now I have this question. The blue curve is given by r of x equal f of x minus 10. That's the same f of x that's now in the red curve. That's the same f of x we looked at, except now I define this as f of x minus 10. I subtracted 10 out of it. Now locate the root r of x equals 0. I defined a new function based on the previous function f of x, and now I subtracted 10. Now locate the root r of x equals 0. So obviously what you would do is draw a line at y equals 0, and then pinpoint the root, and lo and behold, the root is the same as f of x equal 10. So the root of r of x equals 0, where r of x is f of x minus 10, is equivalent to the root of f of x equal 10. So what we did here is a little trick where we changed the form of the equation for which we want to find the root. And the value of the root did not change simply by moving 10 to the left-hand side. So in other words, what we did, we said f of x equal 10 is equivalent to solving f of x minus 10 equals 0. Now f of x minus 10, that's called the residual form of an equation. In general, the root of f of x equal alpha is the same as the root of r of x equal f of x minus alpha equals 0, where r of x equals 0 is called the residual form. Now here's an activity for you. Write log x plus cosine x squared equals 3 in residual form. Take a minute. The solution in this case is simply you subtract the right-hand side from the left-hand side, so you get log x plus cosine x squared minus 3 equals 0. So log x plus cosine x squared minus 3, that's the residual function. And once you find the root of that residual function, r of x equals 0, that gives you the root of the original equation. Okay? So now let's go back to our parachutist example. For a specified mass, m is given, a specified velocity, u is given, and specified time, t is given for our parachutist. Write this solution, this equation, in residual form. Remember, our goal is to find c, which is the root of this equation. But now we have this u of t, which is non-zero, so we want to rearrange this equation in residual form. Take a minute to do it, a couple of minutes. Okay, the solution here is simply you subtract u of t from the right-hand side from the equation. Now remember, u of t is going to be a specified value. Okay, so it's equal to alpha essentially in the example we saw before. So r of x, that's our residual function, is mg over c, 1 minus etc. minus u of t, and r of x equals 0 gives us the value, or r of c in this case, there's a little typo over here, so this should be r of c equals 0, gives us the root or the value of c for which u, m, and g that are given to you are satisfy this equation. Okay? All right, so as you've probably now concluded, for the vast majority of situations, we're going to need numerical methods to compute the roots of nonlinear equations. Some characteristics of these nonlinear solvers is that, we may have, or nonlinear equations for that matter, they may have 0 to many solutions like we saw in the previous example. You may have one or more roots or no roots at all. Solution methods are generally iterative and require an initial guess, and we're not guaranteed to find a solution. The initial guess can be critical to finding the solution, to converging to the solution. And bad initial guess may lead to no convergence or convergence to the wrong root, for example, if you have multiple roots. To solve for the roots of f of x equals 0, if you want f of x equal alpha or a, then write in residual form and then solve for residual form equals 0. We will approach this from two classes of solutions: closed domain methods and open domain methods. Closed domain methods are based on the idea that you have an indication of where the root is located. So our initial guess is going to bracket that root, one to the left of it, one to the right of it, and then we're going to keep refining this interval, A, B, let's say, and keep shrinking this interval until we home in on the root. These are quite simple and robust. However, they require you to bound the root, which is not practical in heavy scientific computing applications, because it still requires a visualization or an idea of where the root is located. Okay, now this could be problematic if your bounds end up bounding multiple roots. Okay. Open domain methods, on the other hand, just require an initial guess, not a bracket, just throw in a guess and then see if we converge to the root. They are more efficient, but they're less robust than closed domain methods, and oftentimes they can fail. They can get stuck in local minima or maxima.